So I am very happy to welcome Konstantin Eder for today's talk from the Institute for Theoretical Physics from the Erlangen-Nuremberg University. And he will tell us today about supergravity and the couplings of fermions to loop quantum gravity.
Yeah, thank you very much. And also thank you very much to the organizers for the invitation and for giving me the opportunity to present this work, which I've done in joint collaboration with Hanno Salman, and which results you can find in these papers. Now, does it work? Now, at the beginning, I will give a very broad introduction to loop quantum gravity. And in particular, I will focus on the status quo and the description of matter fields and loop quantum gravity. And in this context, I will also point out the various subtleties in their description. Then I will turn towards a more unified description of matter and gravity, which is actually the focus of my work, and which is based on a principle called supersymmetry. And in fact, in my opinion, this is a very interesting topic to study because, as I will explain to you in a moment, supersymmetry leads to a unified description between both bosonic and fermionic matter particle species, and thus may shed a lot of insights on how to treat them in the context of quantum gravity. And also, supergravity theories have very intriguing geometrical properties, which seem to have interesting applications also in the framework of loop quantum gravity. Now, loop quantum gravity is the framework of quantum gravity that attempts to retain as much as possible of channel covariance through quantization. And it's based on the reformulation of general relativity in terms of new variables called the Barbero variables. And in this way, it turns out this gives canonical general relativity, the kinematic structure relates to two Young-Mills gauge theory. And based on this observation, one then tries to quantize this theory, borrowing tools from the gauge theory, resulting in a quantum theory in which quantum states can be regarded in terms of string-like excitations of the gravitational field. So leading to the notion of spin network states and the corresponding time evolution called spin forms. And this is a picture of such a spin network state. So spin network states are represented in terms of graphs embedded in the spatial slices of a space-time manifold, which consists of one-dimensional edges, which one-dimensional paths, which are called edges, and which intersect at certain vertices. And these edges carry certain quantum numbers, which are spin quantum numbers corresponding to irreducible representations of the SO2 gauge group corresponding to gravity. Now, so far, this was very, very briefly the quantization scheme of the pure gravitational system. And now I would like to couple the method to a theory. And in fact, there exists various interesting results on how to treat matter fields and loop quantum gravity. And since this is such a vast literature, and actually, unfortunately, I only have a finite amount of time, in the following, I will remain rather superficial and also not be able to explain all the results to this fascinating subject. So I have to apologize already at this point. So it's impossible to do justice. And now, at first, I will say something about the technical details concerning the quantization of matter fields, so gauge fields, fermionic fields, and scalar fields, and the framework of loop quantum gravity, and also we'll say a few words on the respective description in the covariant approach. And then finally, I will also talk about the physical applications. Now, among all matter fields, the description of gauge matter fields turns out to be particularly natural, leading to an effective gauge group given by the direct product of the SO2 gauge group corresponding to gravity and some gauge group G, which corresponds to the Young-Mills gauge theory, which is assumed to be compact. And then we can quantize this theory in complete analogy to the gravitational setting, leading to kinematic observables described in terms of holonomies and fluxes. So in the quantum theory, quantum states are again represented in terms of spin network states, where now the edges carry, besides the spin quantum number J corresponding to the gravity, additional quantum numbers corresponding to irreducible representations of the gauge group G of Young-Mills gauge theory. And to the vertices, one assigns intertriners of SO2 and to the gauge group of the gauge group G. And hence, as a result, it follows that these edges carry, besides quantized geometrical flux, also quantized matter flux, which is measured with respect to electric field E of the gauge group G of the electric field E, canonically conjugate to the kinetic of the gauge field A of the gauge theory, which is smeared over two-dimensional surfaces, a complete analogy to computational setting. And then in this framework, it follows that, for instance, in the case of G equal 1, the charge is quantized in the theory. So in this framework, it follows that charge is naturally quantized. And also studying, for instance, the commutation relations between the connection A and magnetic fields made over one-dimensional loops, one finds some interesting relation between the topological Gauss linking number between these loops and the commutation on the commutator. So there's some nice relation between topological relation between the Gauss linking and uncertainty principle. And also there exists results on quantizing gauge matter fields in the context of spin form models. For instance, regime 5 have studied the lattice gauge theory of gravity spin form. And so far, this was gauge matter fields, then also the quantization of fermionic matter fields have been considered in canonical loop quantum gravity. And also these appear to be quite natural in this framework. And based on the early works of Lorelli and Morales de Cotle, one finds that fermions, as one might expect, are located at the open ends of spin network states. And this has been worked out in some detail by Kasnov and Thiemann. And the resulting picture actually depends on the treatment or on the distribution of densities on the fundamental variables of the theory. So for instance, Bayes Kasnov studied a framework in which density is treated in an unbalanced manner. So one considers the components of the fermionic field in terms of scalars, so that the canonical conjugate momentum is defines a density of rate 1. So in the quantum theory, the fermion components are localized, the quantized fermionic degrees of freedom are localized on the boundaries of on the endpoints of a spin network edge, and the corresponding canonical conjugate momentum is defining a density of rate 1 is integrated over three-dimensional volumes, and fixing some reference point, and then parallelly transporting it to any other point of the chosen volume, in order to get a covariant quantity which transforms covariantly under gauge transformations. And then one results in a closed algebra which can be used with quantum theory. But due to the unbalanced treatment of the density, it turns out that it's hard to properly implement the adjointness relations. Because, for instance, one can consider a Dirac fermion, and in that case, chi corresponds to some y component of the Dirac fermion, and pi corresponds to the other part, and both are related by a complex conjugation. And so in this framework, it turns out to be quite hard to implement these adjointness relations in the quantum theory. So Thiemann has considered a different proposal by treating density in a balanced manner. And in that framework, one considers half-densitized fermionic fields. And in that case, one finds that the quantized fermionic degrees of freedom of corresponding to psi and those to the canonical conjugate momentum are both localized at endpoints of a spin network edge. And one obtains some discretized commutation relations. And due to this equal treatment of both variables, one finds that one can indeed consistently implement the adjointness relations. And also the quantization of fermions in the context of spin form model has been considered, for instance, by Bianchi et al. And there one also finds some intriguing picture of the quantization of fermions by considering, for instance, while fermions coupled to gravity, then by discretizing the covariant derivative in terms of finite sums, one finds that also here fermions are now localized along edges of a spin form, and also intriguing formula for the transition amplitudes has been obtained. And finally, also the quantization of scalar fields has been considered, but in contrast to the gauge matter fields and fermionic fields, their quantization appears much more or less natural. And there indeed exist various possibilities how to represent them in the quantum theory. And one possibility is, for instance, has been proposed by Thiemann, who considered point holonomies. So one has some real valued scalar field and associates to it the corresponding exponential e to the I lambda phi of scalar field phi evaluated at some spatial point, and lambda is some arbitrary real number. And since the canonical conjugate momentum defines a density of rate 1, one integrates this over a three-dimensional volume with some smoothing function f. And again, one ends up with a closed algebra which can be used for quantization. So in the quantum theory, it follows that the quantized scalar field is again localized at the endpoints of a spin network edge, labeled by some real number lambda. Yeah. Now, this representation may be regarded as the momentum space representation, in which it turns out that the scalar field phi cannot be implemented as a proper operator in the quantum theory. So a different quantization scheme has been considered by Lewandowski and Salmon, in which now the scalar field is represented in terms of, at a certain spatial point x, is represented in terms of a multiplication operator in the quantum theory. And the canonical conjugate momentum is represented by the exponentiation. By exponentiation, in that case, this XY translation. So this representation may be regarded as the position space representation. And finally, there also exist other possibilities by treating, for instance, scalar fields similar to fermionic fields. So treating density in a balanced manner, so in terms of half densities. Now, so far this was about the technical details. Now to quantize matter fields and loop quantum gravity. And now in the following, I would like to also say some few words about physical applications. Oops. Now, using this quantization scheme, it turns out that considering the Hamiltonian constraint of the meta-coupled gravity system, this Hamiltonian constraint can be implemented in terms of well-defined operator, in particular finite operator in the quantum theory. And this is heavily based on the quantization of gravity via spin network states and the position of diffeomorphism invariance. So in this framework, it follows that gravity naturally serves in terms of a regulator of matter fields in quantum gravity. Also, in the canonical approach, it turns out that the description of time evolution in quantum gravity is particularly hard to describe. And so it turns out that this can be resolved if one couples gravity to matter fields, so that matter fields in this model serve as kind of a reference frame. And this has been worked out, for instance, in the field theory by Orelli, Dietrich, Giesler, and Thiemann. And there it turns out, for instance, by considering gravity coupled to the dust matter fields, that this leads to a proper physical Hamiltonian, which then can be used to study time evolution. And also phenomenological implications of this theory has been considered for studying meta quantum field theories on quantum space-time. And Pullin, Gambini, Salmon, and Thiemann have studied a model for studying, for instance, product states on a quantized meta-coupled gravity theory, and then taking expectation values in the gravity sector. Then one finds that this leads to effectively to a lattice field theory on an effective semi-classical space-time. And interesting observes that this leads to modified dispersion relations, which may have interesting phenomenological implications. And similar considerations have been done in context of cosmology by Arstecker, Kaminsky, Lewandowski. And also there exist very interesting results in the derivation of this model in three-dimensional gravity by Friedel and Levin. We've studied the path integral of a system consisting of a matter field coupled to in three-dimensional gravity. And by integrating out the gravitational degrees of freedom, one observes that this leads to an effective action corresponding to a non-commutative quantum field theory. And last but not least, also Small et al. Has considered an interesting model by deriving matter topologically from Bernardin and Brady. So encoding matter fields in the topology of a spin form. Okay, so far this was about matter fields. Are there questions so far? Okay, so far this was about the quantization of matter fields in a framework where both matter and gravity are described in completely different and described as completely different entities. So gravity and matter are treated as completely different, completely differently in these quantum theories. But interestingly, it turns out that there exists a formalism leading to a unified description by incorporating a fascinating principle called supersymmetry. Interestingly, look on gravity, this leads to a very beautiful geometric description of the meta-coupled gravity system, which I would like to now explain to you, which may shed a lot of insights now to quantize the framework of loop on gravity. And this is what I'd like to explain to you in what follows. So in the following, at the beginning, I will say something, give a brief review on supersymmetry, and then I will talk about the status quo of treating supersymmetry in the context of loop quantum gravity, and then finally I will explain to you the goal of my work and which results. Now, in quantum field theory, there exists the famous Coleman Monolith theorem, which states that the most general Lie algebra of symmetries of the S matrix of interactive quantum field theory is given by the direct sum of Lie algebras given by the Lie algebra, so Lie algebra of spacetime symmetries, plus some Lie algebra of internal symmetries, which could be, for instance, gauge symmetries. And in particular, there's a direct sum of Lie algebras, so there's no mixture between both symmetries. And so it turns out that the only way around this seems to be if one introduces a new kind of symmetry. And this was the result of Hartog, Chansky, and Sonius, who found that the only way this theorem can be overcome if one introduces a new kind of symmetry based on so-called super Lie algebras, which are Z2-graded algebras, G with a bracket, where G decomposes into an even part G0 called the bosonic part, and some additional fermionic part G1. Together with a commutator which restricts to the standard commutator on G0 and the anti-commutator on G1, together with a graded Jacobi identity to be satisfied by this algebra. And then studying these kind of superalgebras, one finds that the smallest possible superalgebra that contains the spacetime symmetries is given by the so-called super-Poincare algebra in case of a vanishing cosmological constant, or the super-ended de Sitter algebra OSP1/4 in case of a non-vanishing cosmological constant. In both cases, the super Lie algebra decomposes in this way, where the even part G0 is the standard Poincare algebra generated by infinitesimal spacetime translations Pi and Lorentz transformations Mij. And the fermionic part is now generated by some fermionic generator Q alpha, which turns out to be a Majorana-Spino. And this Majorana-Spino now satisfies these additional graded commutation relations. And in case of a non-vanishing cosmological constant, these require additional contributions corresponding to some length scale L, which is the so-called under de Sitter radius. So in this setting, it follows that this additional fermionic generator is anti-commuting and particularly transforms as a spinor. So as a result, it follows that this relates particles of both integer and half-integer spin. So it relates bosonic and fermionic particle species. So quantum field theory satisfying this kind of symmetry naturally leads to a unified description between both force and matter particles. And also one can include, of course, further fermionic generators to the theory. So in that case, this generator Q alpha is labeled by some additional label R, which is called the R symmetry index. It takes values from 1 up to some integer n, in which case one calls this an extended supersymmetry. Also, this can be applied in the context of gravity by posing a principle called local supersymmetry, and then this leads to the notion of supergravity. For instance, the easiest possible model of supergravity model is given by the n=1, d=4 supergravity theory, which now, besides the bosonic gravitational field, contains an additional fermionic contribution corresponding called the spin 3/2 Richter-Schwinger field. So this theory leads again to a unified description containing both a bosonic matter field and a fermionic matter field. Now, also there exist various results on how to treat supersymmetry in the context of loop quantum gravity. For instance, the canonical description of supergravity using Ashtika-like variables has been first time considered by Jacobson, or also has derived an additional constraint in a theory called the Susy constraint. And then later, this has been extended by Philip, who studied the constraint algebra between the Gauss and Susy constraint. In that case, it turns out that this forms indeed a proper subalgebra corresponding to an enlarged gauge symmetry called the OSP1/2 gauge symmetry. And based on this observation, then constructed a connection, OSP/2 connection. And then using this connection, a formal quantization of the theory has been proposed by Gambini, Obregon, and Pulin, and also Ling and Smolin. And also this observation has been used in context of D=3 spin form models mainly by Levine and collaborators. We use this model in order to get an idea how to quantize fermions in the context of spin form models in modern gravity. And finally, more recently, Bodendorfer, Thiemann, and Thurn succeeded in generalizing the canonical description of supergravity theories to higher spacetime dimensions by introducing Ashtika-like variables. Also, the quantization of Richter-Schwinger field has been proposed, as well as the quantization of B-form gauge fields, which play an important role in higher dimension supergravity theories. Now, the goal of my work is to follow the ideas of Ling and Smolin, and try to keep supersymmetry as manifest as much as possible in the canonical theory. In particular, in this context, I would like to answer the question where this enlarged gauge symmetry one observes in the constraint algebra actually comes from. In particular, I want to understand the geometric origins and also with a few towards generalizations. In particular, I want to understand for which values of the Barbero-Immirzi parameter this enlarged gauge symmetry really appears, and whether this can be also extended to supergravity theories with extended supersymmetry. And also in this context, it turns out that the study of boundary theories is a particular interesting question, which can be used then to study quantum PBS states and the quantum properties of black holes. In particular, I want to do this in a mathematically rigorous manner, both in the classical and the quantum theory. And therefore, we study the structure and properties of graded holonomies and also the structure of quantum Hilbert spaces. And there it turns out there exists some interesting relation to the standard quantization scheme of fermions and independent gravity, which I would like to explain. So in this talk, this talk is divided into two parts. In the first part, I want to talk about the classical theory. So I want to explain the interpretation of supergravity in terms of super-Cartan geometry. Then I will derive the Holst MacDowell-Mansouri action of supergravity for arbitrary Barbero-Immirzi parameters. Then I will talk about the extension of this to include supergravity theories with extended supersymmetry. And then I will also point out special properties of the boundary theory, because this tends to be quite interesting in this geometric approach. And finally, we'll point out special properties of the self-dual theory. And at the end, I will talk also about the quantum theory, so the construction of Hilbert spaces, and then also possible applications, context of loop cosmology and black holes. All right, are there questions so far before I go over to gravity and supergravity? Okay, then let me proceed. Now, actually, I will explain this maybe in a few words at the end of my talk. So towards the end of my talk, because in order to properly describe the incorporate the anticommutative nature of fermionic fields in the theory, the classical theory, it turns out that actually one has to consider an enriched category of supermanifolds. So actually, I will consider supermanifolds which are parameterized by some additional parameterization supermanifold, which encodes the fermionic degrees of freedom. I will not explain this in any detail, I'll just say that there is some new feature one obtains if one studies matter field theories with anticommutative degrees of freedom. Actually, this has some very interesting properties, and I will explain this in the context of loop gravity at the end. So before I go over to supergravity, now let me give you a review on the description of gravity in terms of a Cartan geometry, because this turns out to be nicely extendable to the supersymmetric setting by just moving everything to the super category. Now, Felix Klein studied the famous idea to classify geometry of space by the underlying group of symmetries. For instance, you could consider Minkowski's spacetime, and then you can consider the isometry group, which is given by the Poincare group. If you then fix a certain spacetime event P, you can consider the subgroup of isometries which preserve that point, which is given by the Lorentz group. If you then take the coset space between the Poincare group and the Lorentz group, you find that this is manifold is indeed diffeomorphic to Minkowski spacetime. So it follows that Minkowski spacetime can equivalently be described in terms of the underlying group of symmetries. And so based on this observation, Felix Klein, one defines a Klein geometry now in terms of a pair GH, where G is a Lie group and H is a closed subgroup with the additional requirements the coset space is connected. So as one sees, flat spacetime is the current description in terms of a Klein geometry. And based on this observation, Cartan formulated a theory which is now known as a Cartan geometry, which can be regarded as a deformed Klein geometry, just as gravity can be described as a deformed version of flat Minkowski spacetime. And here I've written down the main definition of a Cartan geometry. So a Cartan geometry is modeled on a Klein geometry GH corresponding to the flat model. and which is described in terms of a principal H bundle P. So P can be regarded as the deformed version of the Lie group G. And on this deformed Lie group, there is defined the connection A, which is called the Cartan connection, which takes values on the Lie algebra of G. And the degree of deformation is encoded in terms of its connection A, which has to satisfy these additional properties. And the last property is the most important one, which is the so-called Cartan addition, which leads to local identification of the tangent spaces of the deformed Lie group to the Lie algebra of the Lie group G. And then using this this connection, one can then apply this indeed to a context of gravity. So we now would like to describe gravity in terms of Cartan geometry modeled on anti de Sitter space. So given by the isometry group of anti de Sitter space and the stabilizer subgroup given by the Lorentz group. And then one can take the Cartan connection and decompose it by projecting on the translational part, which gives the soldering form E, or called coframe, and an additional part by projecting on a Ransome part, which gives the Lorentz connection omega. Then using this connection, one can then formulate an action principle. And the idea, and I would like to do this in the context of loop on gravity by including a finite Barbero-Immirzi parameter. And the idea to derive the Holst action by MacDowell-Mansouri has been proposed first time by Derek Weiss and Rondono in the context of perturbed BF theory by Friedel and Stavropoltsev. In this context, I would like to discuss this in the context of anti de Sitter gravity, because there you can use the identification of the symmetry algebra via the algebra of the symplectic group in 4 dimensions. Because in that case, it follows that the Lie algebra, Lorentz algebra can be, the generators of the Lorentz algebra can be expressed in terms of gamma matrices. And then using this representation, one can introduce a beta-dependent Clifford algebra element on the algebra, which acts on this algebra, so beta is the Barbero-Immirzi parameter. And then using this operator, one can introduce an inner product, a beta-dependent inner product on the algebra, by contracting this operator with a trace. And then using this beta-dependent inner product, one can formulate an action principle, which turns out to be of Yang-Mills type. So one takes the curvature of this connection A, Cartan connection A, is an arbitrary type action, and contracts the internal indices using this beta-dependent inner product. Then by decomposing it, one finds that this leads to indeed the Holst action in the bulk, plus some additional boundary terms. Okay, so far this was the interpretation of gravity in terms of Cartan geometry and the derivation of the Holst action via the MacDowell-Mansouri gravity action. I would like to extend this to the supersymmetric setting. And in this context, I will also talk about the boundary theory, because the boundary theory turns out to be particularly turns out to be very special in this context. So I just move everything to the super category and describe ADS supergravity as a super Cartan geometry, which is modeled on the superclient geometry corresponding to a super anti de Sitter space. So we have the isometry algebra OSB1/4 and the stabilizer subgroup, which is given by the spin group. And then we have again a super Cartan connection, which is defined on this bundle and which take values in the algebra of this super anti de Sitter algebra. Then again, we can use this connection and decompose it by projecting on the fermionic part and the bosonic part of the Lie algebra. So in the bosonic part, one gets again the soldering form E and some spin connection omega. And for fermionic, and since we now have additional fermionic contributions, we get some fermionic component in the connection A, which is the so-called spin 3/2 Richter-Schwinger field. So in the supersymmetric setting, it follows that the geometric description and this Cartan connection now naturally includes both gravitational and matter degrees of freedom. And then using this connection, one can again formulate an action principle. And I now would like to discuss this by introducing a beta-dependent inner product, similar to the case of gravity. So now we use the fact that the super anti de Sitter algebra contains additional fermionic contribution, which naturally defines a Clifford module. So we can naturally extend this beta-dependent Clifford algebra element to the whole super algebra by just adding an additional copy of B beta, so that this it's an operator B beta on the super anti de Sitter algebra. And then using this operator, we can again define a beta-dependent inner product, projecting this operator with the super trace. Then using this beta-dependent inner product, we can again formulate an action principle, which is again of Yang-Mills type. So it's an R type action with R the Cartan curvature of the super Cartan connection and the internal indices contracted with the beta-dependent inner product. And again, by expanding this, one finds that this indeed leads to d equal 4 n equal 1 ADS supergravity plus some additional boundary terms. And now these boundary terms turn out to be quite special in this context. Because one may ask the question, what is so special about the boundary terms which are contained in the one to naturally appear in the superhouse MacDowell-Mansouri action? And therefore, one may write down the most general ansatz of possible boundary terms which are compatible with the symmetries of the Lagrange. In that case, one finds that the most general ansatz is given by the sum of 4 individual terms, given by the Gauss-Bonnet term and the Pontryagin term, and some additional boundary terms corresponding to the fermionic degree of freedom, and the C's arbitrary constant coefficients a priori. And then one may impose the important condition that by adding this boundary term to the Bach theory, that the full theory is still invariant under supersymmetry transformation, in particular invariant under supersymmetry transformations at the boundary. And this question has been first time considered by Adrianopoli and Doria and collaborators in a series of works. And now it turns out that if one studies this condition, though supersymmetry invariance at the boundary, this leads to additional boundary contribution of the full Lagrangian. And then by studying this additional boundary contribution one obtains from this principle, it turns out that this boundary condition uniquely fixes the boundary terms to be added to the Lagrangian. So these coefficients C, which are completely arbitrary, are now fixed to specific values. And we have studied this in the context of Holst supergravity, and we then end up with this unique boundary term. And interestingly, by adding this boundary term to the Bach theory, one finds that this exactly reproduces the boundary term of superhouse MacDowell-Mansouri action. So to summarize, requiring supersymmetry invariance at the boundary uniquely fixes the boundary terms, and by adding this boundary term to the Bach theory, this leads to the superhouse MacDowell-Mansouri action. And now I may ask the question, can this also be extended to include supergravity theories with extended supersymmetry? And the answer is yes. And we've considered this for the case n equal 2, in which case now the super-Cartan connection now acquires is of this form and acquires an additional G1 contribution called the graviphoton field. Again, one may write down the most general form of the boundary theory and impose the condition that by adding this boundary theory to the Bach theory, that the full theory is still invariant on supersymmetry transformation at the boundary. And in the context of usual variables, this has been considered by Adrianopoli et al. And we have extended this to include Holst supergravity. In that context, it again turns out that the boundary theory is again fixed uniquely by this condition of supersymmetry invariance at the boundary. And by adding this to the Bach theory, that the full theory is again of this type. So again, end up with the Holst MacDowell-Mansouri type action, which is an RHR type action, contracted with some beta-dependent product where P beta is now an operator on the space of super Lie algebra value 2 forms in the manifold. And this operator now contains some additional contribution on the U1 sector. And interestingly, this depends this contains some theta topological term, which is proportional to the Barbero-Immirzi parameter. So in this framework, beta literally has interpretation in terms of a theta ambiguity in the theory. So again, imposing supersymmetry invariance at the boundary uniquely fixes the boundary theory in the context of Holst supergravity leads to the superhouse MacDowell-Mansouri action. Are there questions so far?
Yeah, if I can ask you a question. If I remember, there's an interpretation of the Immirzi parameter as adding a topological term to the action with the Ni-Yang invariant. Is it more or less related to the boundary terms that you look at, or is it different type of terms?
Yeah, it's a different type of term. So this term is really topological if you even do not impose any equations of motion. But the fact that this appears is actually quite related to this beta, this topological term appearing in the purely bosonic theory you mentioned, I think. So this beta-dependent term, source term in the bosonic theory is related to this term because if you study the supersymmetry transformations, you see that the supersymmetry transformations at the boundary arising from the U1 sector actually exactly cancel those from the gravitational sector if you include this boundary term. So in this sense, they are related.
And I had a little another question. Adding all these fermion fields, you still get only one parameter Immirzi ambiguity, or you don't get any extra? Is it because the supersymmetry really protects against extra complete constants, or?
Yeah. So in the sense, all this principle of supersymmetry invariance requires that the theory is described in terms of a single new parameter. So you can get any new parameter in the supersymmetric setting. And this follows from this geometric description coupled with the supersymmetry, with the principle of supersymmetry.
Okay, thanks.
Other further questions? Okay, then let me proceed. Now it turns out that since this operator b beta actually this operator b beta in this action principle, it does not commute channelly with arbitrary gauge transformations corresponding to the channel super untitled algebra. So the theory is actually not a proper Young-Mills gauge theory, but only invariant under the Lorentz subgroup. But now this changes drastically in the context of the chiral theory, because in that context, it turns out that this operator p minus I corresponding to beta equal plus minus I now becomes a proper operator, proper projection operator on a super algebra of the super untitled algebra. So, so for n equal 1, inferring follows that this operator projects the Lorentz transformations Mij to some chiral component Tr plus and the Majorana fermions to some chiral components Qa. And then studying the algebras, and then studying these generators Tr plus and Qa, one finds that these indeed generate as proper subalgebra of the super untitled algebra, which is called the which is the so-called OSP1/2 super untitled algebra, corresponding to antecedent space. So, to this fact that this is now a proper projection operator on a sub-super algebra, it follows that the super Holst MacDowell-Mansouri action in this chiral limit now is manifestly invariant on a large gauge symmetry given by the OSP1/2 gauge symmetry. And now, interestingly, something similar happens in the case of n equal 2 extended supersymmetry. So, in this framework, supersymmetry now partially becomes the true gauge symmetry of the theory. And then, using this fact, one can one can apply this this projection operator and apply this on the super Cartan connection, and answer with the connection A plus, which one may call the super Cartan connection, which contains in the bosonic part the self-dual connection A plus, and the chiral components of some additional Fermion contribution corresponding to the some Y component, chiral component of the Reiter-Schwinger field. And then studying this connection A plus, one finds that that for both cases n equal 1 and n equal 2, the super Holst MacDowell-Mansouri action can be split in this way. So the bulk action is again of BF type. So the E is the so-called superelectric field, which is the canonically conjugate variable of the superelectric connection A plus, M, which is built up some graded symplectic phase space, and one ends up with additional boundary contribution, which now, which I said earlier, is uniquely fixed by requiring supersymmetry invariance at the boundary. And in the context of the chiral theory, it turns out to be of Chern-Simons type. So we have a boundary theory is a Chern-Simons theory, OSPN/2 Chern-Simons theory with complex Chern-Simons level K. Now, also one can consider the boundary conditions, and one finds that this is again in complete analogy to the classical theory. And one finds that this leads to a coupling between the curvature of the connection on the boundary to the superelectric flux in the bulk. So as we see, the superelectric connection seems to be a natural candidate to quantize supergravity and low quantum gravity, and also turns out to even exist for extended supersymmetry. And by its very definition, it contains now both gravity and matter degrees of freedom. So it leads to a unified description of both, and also to a more fundamental way of quantizing fermions into quantum gravity. Interestingly, it also substantially simplifies the constraints, because it's, some part of the supersymmetry can be implemented in the quantum theory by simply imposing gauge invariance. And also in the chiral theory, it turns out that the boundary theory is described in terms of a super Chern-Simons theory. So it seems to be a natural candidate to study inner boundaries into quantum gravity, in particular supersymmetric black holes and quantum PPS states. And interestingly, there are some interesting relations to description of boundary theories in the context of string theory, because in the recent works of Mikhailov and Witten, one observes that the boundary theory for certain string and brane configurations, that the boundary theory is also described in the super Chern-Simons theory with OSP gauge group. I will say something about this at the end. On the following, I would like to use this superarchitect connection A+ and adapt the quantization scheme using standard tools of loop quantum gravity. And now, so in the following, at the beginning, I would like to give you a brief review on the quantization scheme and the bosonic theory. Then I will extend this to the supersymmetric setting. Now, in the bosonic theory, we can use the fact that the connection A+ defines a gauge field, so we can use it to associate to it anomaly or paratransport map along one-dimensional path E, given by the path ordered exponential of the connection A+, integral of the connection A+ along the path E. And then considering a finite graph gamma, which consists of a finite collection of these edges C, which are now then called edges, we can then use this holonomy, which then leads to a covariant functor on the path groupoid generated by this graph gamma to the gauge groupoid G, which then associates to any edge E contained in this path groupoid the corresponding holonomy. And then considering all these possible covariant functors, one ends up with a set A gamma, which is called the set of generalized connections. But a priori, the choice of the graph gamma is completely arbitrary. So one actually has to consider all possible graphs. And then one ends up with a projective family, where in case that the graph gamma is contained in a larger graph gamma prime, one has a projection of the set of generalized connections associated with the graph gamma prime to the set A gamma. And then using the whole family of generalized connections labeled by graphs gamma embedded in C on the spatial slices of the manifold, these then serve as a starting point for quantization of the enlarged Cartan-Ivanovsky. And this can be done by associating to it an inductive family of pre-Hilbert spaces. So to each graph gamma, one associates an Hilbert space, pre-Hilbert space H gamma, defined in terms of smooth functions on a set of generalized connections. And then using the fact that these Hilbert spaces can be identified as the space of smooth functions on modulus E of gamma copies of the gauge group G, where modulus E of gamma is the number of edges defining that graph gamma, we can then use the Haar measure on the Lie group G to induce an inner product on the pre-Hilbert space H gamma. But this cannot be done arbitrarily, but actually has to be done in a way such that this is consistent with projections. So one has actually imposed a cylindrical consistency. So we need to include the consistency on the change of the graph. Okay, so far this was the purely bosonic theory. I would like to extend this to the supersymmetric setting. And therefore would like to study this superarchitect connection A+ and study the corresponding holonomies. But now in this framework, it turns out in order to consistently resolve the uncommutative nature of fermionic fields, one actually has to include an additional parameterization to the manifold S. So in order to encode the fermionic of freedom, actually one has to include some parameterizations for manifolds. One has to work in this enriched category. Then it turns out that super holonomies are not described in terms of group elements, but rather in terms of morphisms from the parameterization to the gauge group G. And A+, so A+ here now decomposed into an even part, which is given the bosonic self-elastic connection, and the certain from fermionic contribution corresponding to the Richter-Schwinger field. And interestingly, this parameterization is now really mandatory, because in case that this parameterization S is chosen to be trivial, one finds that these fermionic contributions simply drop off, and this connection reduces to standard bosonic holonomy corresponding to self-elastic connection A+. So this parameterization S is really significant if one would like to resolve the uncommutative nature of fermionic fields. And so this encodes the fermionic degrees of freedom. In case of a trivial parameterization, one recovers the bosonic theory. And then studying these kind of holonomies, one finds that the set of generalized superconnections, besides the graph gamma, are now labeled by some additional parameterization S. And again, as in case for the graph gamma, this parameterization S is a priori chosen completely arbitrarily. So one actually has to consider all possible parameterizations. And then it follows that actually one has not just these arrows, but actually squares. So the vertical, these horizontal arrows correspond to the change of the graph, and the vertical arrows correspond to the change of parametrization. And this can be done in a consistent manner, so one gets actually commutative diagrams. And now by fixing a certain graph gamma, this interesting naturally induces a functor for mapping a parametrization to the set of generalized connections. And these objects actually have a name. These are so-called Molokov-Saxon supermanifolds. And then using this identification, one can then study the cylindrical functions and also invariant measures on these sets. And one finds that this, due to the requirement of covariance and the change of parametrization, that this requires a Berezin type integral for the fermionic degrees of freedom. So the parametrization naturally leads to the to a fermionic to the Berezin integral on the fermionic degrees of freedom, which is the standard measure one uses in the standard quantization scheme of fermions in low quantum gravity. Interestingly, it turns out to be a strong similarity in this description and the standard quantization scheme of fermions in low quantum gravity. And this I would like to explain in this slide here. So actually we can reform. So we consider now the standard quantization scheme of fermions in low quantum gravity, and we would like to reformulate this in a way such this this is formulated in this approach, and this can be done indeed. So we now consider this quantized fermion gravity system in standard low quantum gravity, and there it turns out, as I said earlier, the fermionic degrees of freedom are localized at the vertices of a spin network graph. So we can think of this as a tetrahedron, quantized tetrahedron, with a fermion sitting in the interior. And the Hilbert space associated to the vertex V can be now expressed in terms of a set of smooth functions on a supermanifold, where the supermanifold now is given by the semi-direct product given by the SO2 gauge group and corresponding to the bosonic degrees of freedom, and some additional fermionic part, which corresponds to the Dirac fermion. And this manifold, so that this group manifold G now carries a natural group action given by the group action of the SO2 gauge group on functions defined on that manifold, which is given by the standard transformation of anomalies and the transformation of gauge transformation of fermionic fields. And then studying out the measures which are invariant with respect to this SO2 group action, one finds that the invariant measure is decomposed in this way. So it contains two terms. The first one corresponds to the standard Haar measure of the SO2 gauge group, plus some additional contribution, which is the Berezin integral, so the standard integral on the fermionic degrees of freedom. And actually, this is this inner product is not positive definite, but not positive definite. So we have actually so the semi-direct, semi-definite inner product space, but this inner product this product space turns out to be a Krang space. And then using this structure, we can apply a procedure called Krang completion by completing this to a positive definite inner product. And now this turns out to lead to the quantization of fermionic fields as proposed by Thiemann. So applying this quantization scheme, so we're actually using this quantization scheme of fermions in low quantum gravity. One can rewrite this in terms of supermanifolds, and then applying this quantization scheme I explained earlier in the supergravity context to this model, one finds that this leads to a description of fermionic fields, which is the standard one which uses in low quantum gravity. And I would like to further discuss this in the context of supergravity. But now it turns out that since we work actually with complex variables, the gauge group, underlying gauge group, is generically non-compact. And additionally, we have to deal with indefinite inner product spaces and have to deal with symmetrical consistency. And finally, since we actually deal with complex variables, we have to recover ordinary real supergravity. So we have to solve reality conditions. And even in the context of the bosonic theory, this is an open question. But actually, currently, we are working on a proposal which seems to resolve some of these issues. So we consider now the unitary autosymplectic group, which seems to at least solve the problem of dealing with non-compact gauge groups and the non-positive definiteness of inner product spaces. But finally, we have to deal also with reality conditions, but this is still an open problem in the bosonic theory. but we have managed to solve this in the context of symmetry-reduced model using this enlarged gauge symmetry. And this is what I'd like to explain very, very briefly and what follows. But before I proceed, I would like to ask the question, are there any questions so far? Okay, and let me proceed. So since we have to deal with relative conditions, we would like to consider a symmetry-reduced model in order to find a way to solve these. And indeed, it turns out that there exists some model where you can use the enlarged gauge symmetry. Because normally, if you consider isotropic models, that this seems to be not compatible with the position of fermionic isofreedom. But now, since we have this enlarged gauge symmetry, it turns out that one can use this gauge symmetry in order to have connections which are invariant which are isotropic, and homogeneous and isotropic. And we have done this in the context of chiral supergravity. And we found that using this enlarged gauge symmetry, that the most general ansatz of a connection A plus, superconnection A plus, which is invariant under homogeneous and isotropic, is given by this formula. So due to this large gauge symmetry, we now, besides this homogeneous isotropic self-large connection, which is described in terms of some scalar or some bosonic Grassmann value C, it has some additional fermionic contribution corresponding to the homogeneous isotropic Rita-Schwinger field. And then using this this symmetry-reduced Ashtek connection, we then have quantized the theory using standard tools of cosmology, mimicking standard tools of loop quantum cosmology, and then we end up with a Hilbert space, which is given by the Hilbert space of corresponding to bosonic degrees of freedom and the Hilbert space of fermionic degrees of freedom. And then it turns out that in this Hilbert space we can indeed solve the relativity conditions consistently, and also we were able to implement the constraints on the quantum theory such that the constraint algebra exactly reduces the respective Poisson algebra in the classical theory. In particular, we found that the algebra between the Susy constraints reduces the Newtonian constraint, modulo Susy constraint. Also, we have finally considered the semi-classical limit of the theory, and we found that this leads to the Hartle-Hawking state, which is contained in the solution space of the theory. So to summarize, due to this large gauge symmetry appearing in the chiral theory, the homogeneous isotropic super-Ashtek connection contains non-trivial fermionic degrees of freedom. And using this ansatz, one can formulate a quantum theory in which one can solve consistently the relative conditions and also consistently implement the constraints. And finally, this is some work in progress because, as I told you earlier, so imposing Susy invariance at the boundary uniquely fixes the boundary theory. In context of the chiral theory, it leads to a super Chern-Simons theory. And using this fact, we would like to study quantum properties of supersymmetric black holes in framework of quantum gravity. And interestingly, there exist some related results in context of superstring theory, because in superstring theory, one observes that by studying certain string and brane configurations, that the boundary theory is described effectively in terms of a super Chern-Simons theory, also described in terms of an autosymplectic super gauge group. And we would like to, because now due to these results, now super Chern-Simons theories with a gauge supergroup are now an interesting topic in this field, and lots of work on this. We would like to learn from this to get an idea how to describe them in the context of quantum gravity. Okay, so to summarize, the first part I talked about the classical theory. In particular, I talked about the geometrical interpretation of supergravity in terms of the super-Cartan geometry, and derived the Holst MacDowell-Mansouri action for n equal 1, n equal 2, ADS supergravity, and also pointed out that the boundary theory turns out to be unique if one imposes supersymmetry invariance at the boundary. And the chiral theory turns out to be special in this context because it has the structure of a Young-Mills theory and leads to a super-Ashtek connection. And again, the boundary theory, which is uniquely fixed by imposing supersymmetry invariance at the boundary, turns out to be a super Chern-Simons theory. We have then considered the quantization of the theory, in particular have studied the rigorous construction and of graded holonomies, and also studied their structure and properties. And then we also observed intriguing similarities to the standard quantization scheme of fermions and loop quantum gravity. And then, since we have to deal with relative conditions, we have considered a symmetry reduced model, and that this large case symmetry turns out to be very important because it allows for non-trivial fermionic degrees of freedom. And then, studying this theory, one can indeed solve the relative conditions in a consistent manner. And finally, there are still difficulties in the Cartan theory in order to properly deal with the inductive projective limit, construction of a continuum Hilbert space in the self-driven theory, and also the proper solution of these relative conditions in the full theory. But we have solved them in the symmetry reduced setting, and this gives some hope that this may be also be possible to in the context of the full theory. So in the future, we'd like to further study the Hilbert spaces and the solution of relative conditions, also study observables. Also, we'd like to study the boundary theory and study quantum theory of supersymmetric black holes and framework of loop quantum gravity, and try to find some relations to the respective description of in the context of superstring theory. Also, we'd like to extend our results to include supergravity theories with extended supersymmetry with n greater than or equal to 3. So we'd like to study the boundary theory and ask the question whether the boundary theory is again fixed unically if one imposes supersymmetry invariance at the boundary, and whether this then leads again to a geometric description of these extended supersymmetric theories in terms of a Cartan geometry. Finally, so far we have always considered the a finite cosmological constant. So actually would like to get rid of this cosmological constant setting L to the infinity. Also there exists some interesting results by Concha, Ravera, and Rodriguez, who found that also in this case one has a MacDowell-Mansouri type action of the flat theory. Whether this, the interesting question whether you could apply this to context of Holst supergravity. And yeah, thank you very much.
Well, thanks a lot for the talk. So if anyone has questions. Well, in the meanwhile, I wanted to ask you, you haven't talked about super spin networks, or spin networks based on representations of OSP 1, 2, or N2. Why is that?
Actually, yeah, so you can actually there's various you can of course define a certain subset of states or of which so in terms of superspin network states, so states which can be represented in terms of graphs whose edges carry irreducible representations of the OSP gauge group. But now there are subtleties related to because super Lie groups, or the representation theory of super Lie groups is much more complicated than for ordinary gauge groups. So because even in context of compact super Lie groups, the representations or the irreducible representations not necessarily define a tensor category. So if you study, for instance, you study the tensor product of two irreducibles, this does not lead to a decomposition in terms of other representations in this category. So it actually has to restrict to a subclass. But one may hope that because in the context of the unitary autosymplectic group, in certain cases that these indeed form indeed subcategories. So, and may actually, because if one can study relative conditions in the bosonic theory, and one finds that this leads to some kind of a gauge fixing. This is actually some recent result of Robert Seeger and Hanno Salman. And if one may think that if one extend this to the supersymmetric setting, that this may lead to a gauge fixing in the supersymmetric setting to the unitary autosymplectic group. And this group now has the property that certain subclass of representations form a tensor category. Then one can formulate spin network states and so on and so forth. Yeah, so this is a harder problem in the supersymmetric setting, but it seems to be solvable.
And this problem of a non-reducibility of a tensor product of a representation, how do you see it in your formulation in terms of functions on the group? And like in this next slide, where you say that you have function on the group and on C04. Yeah. What's the problem? Where do you see the problem about?
Yeah, so this is actually you can consider two different models. So if so this model is based on it's a bit differently. So you can consider a set of generalized connections, pointed generalized connections where the fermionic fields are localized at edges or at the boundaries of a spin network edge. And then you find that if you apply this principle, the underlying gauge group is just SO2, so it's SO2, but then you can indeed, so this procedure goes through and you get a positive definite inner product and you get a gauge group which where the UG representations form a proper tensor category which can be used. Yeah, so this is a slight reformulation actually, which I have not expressed in detail, but this is some slight reformulation. And using this reformulation, you can solve these issues. But actually, one has to restrict to a bosonic gauge group again.
Okay. And I also wanted to ask you if this whole reformulation leads to some interesting supersymmetry breaking proposals for loop quantum gravity, because it's one of the criticism we do against usually supergravity theories, that you'd like to break the supersymmetry. And now here we have some models of loop quantum gravity with supersymmetry. So is there some unusual mechanism or some new mechanism that this is going to propose to lead to?
Yeah, so what is special about this approach is that because in the chiral theory, this some part of the supersymmetry is now really a proper gauge symmetry. We can indeed preserve this kind of symmetry in the formalism studying now superspin network states and so on and so forth. So this helps in a way, at least partially, incorporate supersymmetry in this quantization scheme. So this is some special property of the self-dual theory, because there we have this result that some chiral part of the supersymmetry algebra indeed is a proper gauge symmetry of the theory. So this is why this helps at least partially to preserve some part of the supersymmetry. And interestingly, it leads to a quite unified description of matter fields and gravity theory.
Okay, thanks. Is there any other questions?
Well, maybe I can briefly say something regarding this supersymmetry breaking. I think Eder was wondering whether, in our world we observe gravity and fermions, and they look quite different, and we don't seem to be able to transform them into each other. I think I don't have a good answer. We don't have a good answer to how to break this elegantly, but this MacDowell-Mansouri formulation makes me hopeful because it's very neatly packaged. And for example, Konstantin could show that one can get this Holst sort of deformation that gives one the in a sense the super Holst action. And I could see that one can maybe come up with some other natural deformations or something like this of this framework, like on this super algebra level, that could give nice supersymmetry breaking schemes. I could see that since there's a very geometric starting point, that one can invent something from there.
Thanks, Hannah. So if there's no other questions, I would like to thank Konstantin for the talk. And yeah, thanks.
Thank you very much. Bye.
Thank you. Bye-bye.
Bye.
Bye.
Thanks.